Hey, what's up SREcon? How is everybody doing? Oh, what's that? You can't tell me because I'm only pre-recording this in my bedroom and you're going to see the video later on? Fair point. In which case, I hope you're doing well and thanks for tuning in for the video. My name is Pawlikowski, I'm a software engineering lead at Bloomberg and it's my absolute pleasure to be co-hosting this today with the one and only, my friend and co-worker Sachin Kamboj. And we've come to talk to you about this thing called chaos engineering. We've been doing this for a number of years now, and we think that this is something you might like. So here is a 5-year retrospective of what we've learned, what worked and what didn't in our practice and experience. If you like some of that, don't change the channel. I'm gonna start by very briefly redefining chaos engineering to say what I actually mean when I say that, so that we're all on the same page, and then talk a little bit about the evolution, where it started, what it's like, and where it's hopefully going. Sachin is going to cover some concrete examples, things that we actually found that would have been disastrous if we didn't, thanks to chaos engineering, some more lessons learned, and then spoiler alert, it's never been a better time to get started with chaos engineering than now, 2021. So we'll give you some of the things that you're going to need to get started, some tools and pointers to materials. So if that sounds like a plan to you, then let's get started. So first, a deep breath. Chaos engineering is the discipline of experimenting on a system in order to build confidence in the system's capability to withstand turbulent conditions in production. So that's what I consider the canonical definition. You can find it at theprinciplesofchaos.org. This is from the Netflix gang. And it's not a bad definition. Not many big words, nothing to confuse you too much, but still a little bit of fluff. So let's make it even better. Experimenting to build confidence to withstand turbulent conditions. And if the keyword experiment is making you think of white lab coat and protective eyewear and glasses and all kinds of explosives, then yeah, that's what we're after here. Doing some real science to either uncover some things that can go wrong when there are turbulent conditions, in which case we can go and fix them, or building the confidence by discovering that the system is already working well during the conditions. So this is what we're really after. And notice that there's nothing about Chaos Monkey here. So everybody being like, oh yeah, Chaos Engineering, that's just Chaos Monkey. Not really. There's nothing about testing in production either. Nothing about randomly breaking things in production. So these are all things that we kind of hear, and a lot of them are myths that kind of started with the initial communications with, flashy headlines for blog posts. And this is kind of how it works. But none of that is actually in the definition. So when I'm saying chaos engineering, that's what I mean. So let's talk a little bit about where it came from and how it's evolving. So like any other piece of technology, chaos engineering is following a similar path that we call the innovation adoption lifecycle. And it looks like a bell curve, and it basically divides population into buckets. We've got the innovators on the far left side of things. This is the initial part of the population that looks at the technology and is like, oh, this is so awesome, I would like that. And they're ready to put up with all the downsides, with it not being super mature, with the bugs, with the issues, with the rough edges, because they see the value in it. So they go and they adopt that. Once it reaches a bit more of the population, we're talking about the early adopters. So the technology gets better and so more people use it. Eventually we go to early majority, and there's the hump where half of the population has already adopted it, meaning that now in the late majority it's actually more uncommon to not have adopted the technology in question than to have adopted it. And then eventually the last bit, there's always some trailing people who are slower to adopt it, and we're gonna call them the laggards. To give you a familiar example, so we can compare chaos engineering against, think about a mobile phone. So what is it that comes to your mind when I say mobile phone? Presumably something like this, and depending on your age, you might be picturing one of the devices here. You can see some older Nokias, some stuff that you can still practice self-defense with, some more modern Android phones that are more on the smartphone range of things. But if you think about them, probably sort them in order, regardless of the brands. in the evolution from a mobile phone and all the added features later on. What you probably didn't picture when I said mobile phone was this mobile phone. Look at this bad boy, Motorola Dynatac 8000X. Woo! This hot device could not only provide 30 minutes of talk time, but also store up to 30 phone numbers. All of that for under $4,000 in 1983, $84, which is more like 10,000 bucks today. So think about that. Looks a little bit ancient. You can't go on Instagram on it, but you can talk, and 30 minutes is probably enough to describe your lunch that you would otherwise put on Instagram. And it's actually mobile. It doesn't have an attached suitcase with it. You can actually go and claim that this is a mobile phone. And it started something, right? If you compare this to one of the older Nokias from the previous image, they're not that different. The Nokia is going to be a little smaller and it's going to last more than 30 minutes and it's going to be cheaper. But this is something that started the mobile phone the way that we kind of know it today, or at least contributed to starting the mobile phone being what it is today. So if we go back to chaos engineering, at the beginning, there was the Chaos Monkey. As we all know, the famously open source project coming from Netflix. They moved to AWS. They had a lot of VMs, and they wanted to make sure that when their VMs go up and down, their applications keep running. And so they wrote a piece of software that took VMs up and down, and they called it Chaos Monkey. A simplification, sure, but if you think about that, this is the initial innovators, right? They took an idea and sure, Chaos Monkey is rough around the edges, doesn't do much. It's a little bit of a blunt instrument, but it's not very different from what the Dynatac did to the mobile phone, right? It started something, and something concrete went onto the market that could be improved upon. And so people picked it up. People like us at Bloomberg, we wrote a powerful seal a few years ago, Chaos Toolkit, Litmus. There are books about that. I'm going to talk about the tools a little bit later, but the point here is that iteratively, one step at a time, we kept improving on the tools, and so more people could use them, and so they had more ideas how to improve that, and they spent more time using and improving them, and so the tools got even better, and even more people started using them. And this is how the adoption lifecycle curve kind of unfolds, right? So if you think about that, this previous photo with the different smartphones, all of them are improving on their previous models. All of them have added features that not only do mobile phone stuff, but they also do other things. All the way to today's smartphones that are pretty powerful mobile computers sitting in your pocket all day, doing all kinds of things. And then as the time goes by, we keep improving upon them. They get better and better, and we reach the early majority. And somewhere between the early majority and the late majority, we got the hump. That's the 50% mark, where enough of the population adopted it that it's the majority now that does it. And I would argue we're probably somewhere in the early majority still, but getting pretty close to the 50% mark. And the goal of the game is to keep going to the right until we reach the promised land of late majority, where there is eternal holiday. Look how I managed to actually find a photo that has rainbow unicorn that's inflatable on a holiday at the beach. So this is what we want, and that's why we keep improving on the tools and we keep making things more accessible and easier to use. Hopefully that gives you an idea of where we are right now, and let's talk a bit more now about some actual examples from the trenches, some of the things that we actually uncovered that made significant difference to us, that hopefully demonstrate what you too can achieve with that. Sachin, leaving with you.
Thank you so much, Miko. Hello, everyone. My name is Sachin Kamboj, and I'm going to give you some examples from the trenches. These are 4 concrete examples of chaos engineering experiments that we have run, and that allowed us to uncover some bugs that would have caused production outages had we not found them and rectified them beforehand. And the reason for covering these examples is twofold. First of all, it's to show you concrete examples of how chaos engineering has benefited us and how it might be able to benefit you if you apply it. And the second reason is to give you a flavor flavor of the kind of experiments that you can run and what you can learn from them. So let's get started. The first example is, are you really highly available? So typically, if you want to be highly available, you would run n copies of a server. For example, here we have servers 1, 2, and 3, and you have a client that connects to server 1. Now, what happens if server 1 goes down? It might, light on fire, but hopefully it doesn't light on fire. Hopefully it's something as simple as somebody tripping over a cord, a bad memory error, or something else that causes server 1 to go offline. Now, your client should detect this. The latency won't be 0, but it might be a fixed amount and a bounded amount. And then the client should automatically connect to server 2, and everything should continue as is without any problem, right? So that's classically how you would build a highly available system, especially if your 3 servers are stateless. So this is a story from the time when we were in 2016, when we were just playing around with Kubernetes. Kubernetes was the new kid on the block. We had just gone to a conference where they presented it, and we thought, this is cool. We should have a look at this. Let's try it out. This is again before the days of kubeadm and a lot of the other, Kubernetes, the hardware, all the various installation tools and ways in which you can get Kubernetes right now. And if you wanted to run Kubernetes, you had to build it yourself and install it yourself. So this is the experiment that we ran. And, you don't really need to know anything about Kubernetes to understand this experiment. I'll just give you the very TLDR version of what's happening over here. So kubelet is a node daemon. It runs on every single node. It's responsible for starting containers, for managing the lifecycle of containers, for observing containers, for gathering logs from containers. So it does everything on the node for you when it comes to containers. The API server exposes the API of Kubernetes. It's responsible for activities such as authentication and authorization, validation. But more importantly, it's actually a front end to etcd storage, which is your single source of truth, which has everything that should be running in your cluster. So what kubelet does is it contacts the API server and says, give me a list of all the containers or pods that I should be running. And pods are just groups of containers. And then it will schedule those pods and run them on the node. So this is, again, we were starting on very early. And when we were reading the documentation, the flag for kubelet kubelet takes a list of API servers. And it says it takes a list of Kubernetes API servers for publishing events, reading pods and services, comma separated. So we're like, great. Kubernetes is highly available. We're going to run 3 copies of the API server. We're going to run a kubelet. Everything is going to be great, right? So this is very early on. We're starting our one of our very first chaos engineering experiments. And this is very simple. Like, you can do this using Chaos Monkey. You can do this using any number of tools. You just take down an API server. And what we found was that kubelet always connected to the first API server. And if the first API server went down, kubelet would lose connection with the API server and then not be able to do its thing. So this was very surprising. Turns out that these are known issues. There were a couple of bugs that were filed. It's an example of where the intention was there, where when they designed Kubernetes, they thought, yeah, kubelet really should talk to multiple API servers. But then they decided that, typically the way you would expose it is using some kind of a load balancer in front. So we won't actually bother implementing the multiple API servers. And this is just, an incomplete implementation. But again, we would never have found this out until we actually ran an experiment where we tested this out in production. Or, we might have found it out the hard way, where we would have deployed Kubernetes and then the first API server would have gone down and we would have had a production outage. So this is a very trivial example. It was very early in our days of Kubernetes, but it provided us some value, and it taught us the value in doing chaos engineering experiments in general. So our next experiment is an example of what happens when you scale. This is a case of where you have a client or n number of clients, and you have 4 nodes, and you design your application to be web scale. So it's perfectly horizontally scalable. You're a startup, you go out in the wild, and it's wildly successful, and then you start adding nodes. So you add another 4 nodes, and it's even more successful. It's growing, doubling year by year, so you're seeing exponential growth. And then eventually you add a whole bunch of nodes. Let's say you add some 48 nodes, and then one fine day you find out that your client can't resolve DNS. And as the famous saying goes, it's always DNS. So you're like, what's happening? Why is it that, I've designed the application to be perfectly horizontally scalable? I've tested it out, I've scaled it up many times, and yet for some reason, it's still not resolving DNS. It makes absolute sense if you know what's happening behind the scene. What's happening behind the scenes is the client is sending a DNS packet. So DNS by default uses a UDP packet on port 53 with a query that says, please resolve foo.bar.bloomberg.com. And in this case, what really happens is that the number of servers that we get, that the DNS server needs to respond back with, is more than that can fit in a single DNS packet, so it responds with a truncated message. So if you read the specs, the reason they built this, RFC 791 says IPv4 requires a minimum MTU of 576 bytes. Now the IPv4 address is going to include the IPv4 header, which is typically 20 bytes, but can be up to 60 bytes. It needs 8 bytes of UDP header and some overheads. So DNS specifies in RFC 883 that the maximum packet size is 512 bytes. And this is mainly exists to prevent fragmentation of DNS packets because it is transmitted over UDP. So what's happening in this case is that the DNS server responds with a truncated message, and what RFC 5966, which is DNS over TCP, says is that if you get a truncated message, you should retry the message over TCP. So these are two examples where it says the stub resolver must support TCP. Just that the container that we're using was built using Alpine Linux, which is using a version of libc called Musel. And Alpine Linux does not actually support DNS over TCP, which meant that it's not really standards compliant. And it's debatable whose fault this is because, the RFC does say 5966 that stub resolver may omit TCP when designed for deployments in restricted environments where truncation can never occur. So they're thinking that you'll never use Musel libc or you'll never use Alpine in a situation where you need truncation. So they're like, we're perfectly fine. Yet it gets back a response that's truncated and does not know what to do with it. So this is an example where a good way of testing is not just to take things down like Chaos Monkey, but also to try to scale up. Gradually add the number of nodes, see if you can horizontally scale, add the number of clients, add the number of things running on a given node, and see what limits you actually run into. So the third example, this is a very interesting example. It's really dealing with this Kubernetes bug, but I'll try to tell you the story of how we came across this. So we were running Kubernetes version 1.15. And we decided to upgrade to, I believe, 1.16 and 1.17. So anytime we try to do an upgrade, we don't just release it to production and upgrade and say, okay, we hope everything is going to be okay and nothing's going to break. That would be the ostrich approach. What we do instead is we set up a test cluster. We run a whole bunch of chaos engineering experiments to see if everything's working as expected. And we run it for a couple of weeks and make sure we don't run into any issues. So this was an example of, we upgraded to a version of Kubernetes. We ran some chaos engineering, and then we found out that every now and then what happens when we take down an API server is that kubelet says use of closed network connection, and after that kubelet never reconnects to the API server and never recovers. Now, we do know that, there's nothing really wrong because all you need to do is restart kubelet and everything continues working as expected until the next time either etcd or the API server goes down, and then you get a similar set of bugs. So after playing around with it quite a while, we were convinced that it was a Kubernetes bug. So we went to the Kubernetes issues and tried to see if anybody else had seen this bug. And it turned out that, yes, they had. This bug was actually reported on January 28, 2020. And there were lots of reports of lots of people who had seen this bug, but they hadn't reliably been able to reproduce it for a whole year, which is interesting because we actually saw it within like a week of chaos engineering where we were able to reliably reproduce it. So this is a value that you can get from chaos engineering where instead of anytime you do an upgrade, be sure to run some chaos engineering experiments and try to see what breaks. In this case, the bug was actually in the underlying Golang library. So it existed in, I believe, Golang 1.13 and was fixed in Golang 1.14. And the bug was actually fixed in Kubernetes 1.18 when they recompiled against, I believe, 1.14 or might be 1.15. But it's always a fun idea to try to repeat your experiments anytime you're trying to upgrade. And, anytime you get a bug, you can try to see whether you can reproduce it. So reproducing bugs is one thing, or figuring out whether you can upgrade something is great. But there's another reason is, can you proactively go out there and find bugs? This is an example of, it's an etcd cert manager. It's a little component that we wrote to rotate etcd certificates. You don't really really need to know about the component or how it works or anything else. It just uses a variant of a two-phase commit, which is a well-understood, well-used protocol in distributed systems. But when we coded it, we wanted to make sure we did not introduce any accidental bugs in the actual implementation details. So we had this whole, way of how it's supposed to operate in the happy part where everything is supposed to work, and then what happens when there are various failure conditions. For example, a node goes down or a message is lost or any kind of failure conditions like these. So what we did was when we wrote the code, inside the code itself, we introduced chaos points, and those were points at which, either a packet would be considered lost or the etcd cert manager instance would actually crash, panic, or go away. And the whole idea was we deliberately introduced crashes with a probability p at specific points in the code. So we called those chaos engineering points, and there were something like, I believe, 15 or so points in which, different bad things happened while we were introducing it. So we started the experiment and we ran it for like a couple of weeks where we had it randomly crashing at different places, and the ability to reproduce, where exactly it crashed and what was going on at that particular point in time. And that allowed us to find at least a couple of bugs in the implementation and fix them, and allowed us to be sure that, there were no other bugs when we deployed this to production. So this is a very good example of how you can use chaos engineering experiments to be reasonably sure that the code that you're writing is bug-free and well-designed. So what causes of failure is chaos engineering useful for? I would argue that chaos engineering is useful for a whole class of failures. We already showed you node failures and network partitions and how they can be helped. Drop packets is a very interesting one. You can easily drop packets using just a couple of IP table rules, which you can drop packets with a certain probability. And one of the experiments that we run in the past is where we drop, UDP packets with a probability of, let's say, 5% or something like that, and seen what was the effect on the latency. And we found that even if you drop packets with a probability of 5%, due to UDP retries, you don't actually see any error messages into your application, but the latency goes through the roof. So that's an interesting thing to do. We already gave you an example of limits. I would strongly recommend trying other things like, seeing what's the effect on the blast radius. So for example, take down an entire data center or take down an availability zone. But the important thing besides, when testing any of these is to design your experiment really well. So have a hypothesis of what you expect to happen, only change one thing at a time, and try it out and see what happens, and run these continuously, trying to see, what really happens. And with that, I'll pass it on over to you, Miko. Thank you so much.
Awesome. Thanks, Sachin. Thanks so much. So let me cover some of the lessons learned that it might be useful to you. So first thing I wanted to say is that boring happens to be good. And as you can see on the graph that we covered of the evolution, the further you go to the right, the more unremarkable the innovation is, because more and more people have it. So by definition, the further you go to the right, the less hipster and amazing and new it is. But that shouldn't deter you from remembering that that thing that you're holding in your pocket is a pretty powerful computer that people couldn't dream of not that long ago. So boring is good, and boring is particularly good for chaos engineering because chaos is kind of like a double-edged sword in its name, and it doesn't necessarily sit very well with people the first time they hear it. Knowing that it's getting boring is good. Another thing that we discovered over and over is that the experiments tend to be pretty cheap. A lot of these things that we did and a lot of the experiments that were actually useful were super easy to do. Not rocket science, and there's no point claiming that we're geniuses to do that. A lot of that is easy. And that's why it's so helpful for the return on investment when it's so cheap to get started on that. Another thing is that it's just code and should be treated as such. So all of the principles, all of the best practices, all of the things that you do for your other code also apply to chaos engineering code. There's no silver bullet, there's no special treatment for that. The way that you release stuff, you should release that the same way for chaos engineering. All the common sense things that you do to make things work and to keep them working, do them with chaos engineering too. No special treatment. We also found that a mindset shift all by itself was a very worthy addition. Just the fact that people know that their stuff is eventually going to be chaos tested, it's part of the experience, means that there's fewer things that are being swept under the carpet. Because, hey, what's the point if they're going to resurface soon enough, right? The return on investment that we got was ranging from good to awesome. And I know that sounds like a lot, but think about it. A good experiment would be something where we spent a few hours on it and we didn't uncover anything new. And it has this like nice warm and fuzzy feeling inside because our thing actually works already. And the other benefit of that is that once we got that, we can automate it and use it as regression testing. If we modify something in the system, we can verify that it keeps working. So very cheap and provides peace of mind. That's good on my book. And then awesome is when we make an experiment, we design it, we run it, and it turns out that we actually discovered something problematic. And potentially something like the examples that Sachin showed you that could have been disastrous if we didn't catch it or if the clients caught it for us. So the return on investment happens to be pretty good most of the time, even if you don't discover anything new. And then finally, this is probably like a more broad remark than just chaos engineering, but retrofitting is expensive, whether that's your bathroom retrofitting new equipment or a project where you try to retrofit security or chaos engineering. It happens to be much more complicated and expensive the further down the line you do it. So maybe don't do it. So if all of that makes you think, okay, yeah, I should probably give chaos engineering a try now, it doesn't sound that crazy anymore. Well, yeah, that's kind of the point. That's probably what I wanted to succeed, what I wanted to drive home with this presentation the most. But the two things really to take home is that the tools are really available right now. They're open source, some are commercial, but they're there. You can just go and reach out and you'll be able to start within minutes. And the training and books and materials have gotten better. And, you know, I'm going to plug my book in a second, but it wasn't there a few years ago, and now it is. So you can just go and get started. And all of that to say that the cost of entry for chaos engineering is just getting ridiculously low right now. So you really have no excuse to give it a try. So let's talk about the tools really quickly and then the book. If you're looking for a good resource, I recommend the Awesome Chaos Engineering on GitHub. Google should pop up as the first thing. And here's a few select projects that I wanted to mention. Powerful Seal is the project that we wrote a few years ago at Bloomberg, and lets you implement this. You write a YAML file with a scenario where you say, okay, you should do this and this and this, take this down, add latency here, clone this, kill this, take down this VM, and then you do validation. And you run the seal with that scenario, and you can do it on an ongoing basis and verify things. Very easy to start with. Chaos Toolkit, another great example of what open source can offer you. Similar idea. You can write a description of an experiment, including the validation, and run it from command line. Pumbaa, probably worth mentioning. It makes it much easier to work with Docker containers and allows you to do very easily network latency injection, for example, with TC without actually having to learn the horrible syntax of TC. Toxic Proxy, you can stick it in between your application and anything else that it connects to, and then talk to it to tell it to now start injecting latency and now start dropping packets or now start throttling things so that you can see how the application behaves when these conditions actually happen. Chaos Monkey probably doesn't need a description, wouldn't be a complete application without it. Byteman, if you're working with anything running inside of it, the JVM, it's a really great tool that lets you write a small script when you describe what needs to happen inside of a particular class, a method. And then it works as a Java agent, and you can modify the Java code on the fly when it's being loaded and, for example, trigger some exception that would simulate some kind of problem that you expect to see from time to time and see how the system behaves. Really quick to do, don't have to touch the source code. A fun one is KubeDoom that you can plug into your Kubernetes cluster, and then you walk around and shoot at pods, and when they die, you are going to delete pods from the cluster. A very nice thing for demos. And finally, Litmus Chaos, another project that gets bigger and bigger for Kubernetes, integrates with different tools like Powerful Seal, and even lets you now share experiments on their hub. So the bottom line is that the open source tools are there, and they are getting more and more easy to start with. So there is really no excuse once again. And for the training portion of it, here's a plug of my book. It's called Chaos Engineering: Site Reliability Through Controlled Disruption. And it tries to cover all kinds of popular scenarios where you are going to likely use chaos engineering. So anything from how Linux containers work and the underlying Linux kernel functionality, to how to implement your own, how to test things on Kubernetes, how to test Kubernetes installation yourself, how to inject chaos inside of the JVM, or how to do it at the very lowest level of syscalls on Linux, or even all the way up to front-end code with JavaScript, injecting failure there to verify what happens at that level. All of that and more. If you'd like to chat about anything chaos engineering or SRE, here are our QR codes. So you're supposed to be able to scan them and go to our LinkedIn. If you would like photo of Old Phone or Unicorn, here are the awesome people who provided them on us. And finally, if any of this is sounding amazing to you and you would like to go work with people who also think that chaos engineering and reliability are amazing, join us. Bloomberg.com/careers is where you're going to find all the details, and hopefully we'll see you soon. And with that, thank you so much for your time, stay safe, and see you next time.